Hello everyone, so I'll be here for those of you who want to implement some GPU compute shaders for simulations, for example on diffusion reaction or fluids. So this talk was first presented in a workshop, local workshop here in Poland, LBM in Kraków. My name is Maciej Matyka and I work at the University of Wrocław. So the plan for the talk is the following. So first I will tell you a few words about GPU in general, so the way I see it. Then I will move into shaders and tell a few words about why I will use OpenFrameworks and not the OpenGL directly. Then I will introduce you to the technique that I use for implementation of compute shaders. In the example of Lattice Boltzmann Method, but to be honest I will more tell you about the diffusion reaction and then just briefly introduce the tutorial for Lattice Boltzmann. And then there will be some small surprise for my friend Robert, who organized this very nice meeting in Kraków. Okay, so let's start. So what is GPU? So in a few words, GPU, for those of you who didn't really work with GPU before, I will just draw a short picture. So my view on GPU is very simple. We have your usual computer on which you have your CPU, and the CPU can call another processor which is on graphics card, and this is GPU. Now, GPU is a graphics card, means that the graphics card has output directly to your monitor. Okay, so you have your screen and GPU can feed the screen with pixels, so pixels can go there and through, I don't know, HDMI cable. Now, this is important because this link, between CPU and GPU has some limitations on the memory bandwidth and so on, so you cannot really do a lot of copying from CPU to GPU and so on, so keep in mind. But on the other hand, this picture is important because this immediately shows you applications of GPU. So this is very fast here, and if you compute everything on GPU, then you can do very quick, very fast simulations and visualizations directly from GPU to CPU. Okay, let's move on. So the GPU is like this, and that's all. I will not tell more about GPUs. Now, why compute shaders? So compute shaders because you can use CUDA, for instance. Okay, you can use CUDA, you can use OpenCL, you can use many other high-level libraries, but for me the straightforward application of GPU and of computation on graphics card is computer graphics. So then compute shaders are very very natural to use. Also, they are the closest to the graphics pipeline possible. I mean, you can of course use vertex or fragment shaders also for computing, but to be honest, they are not very convenient, and actually that is why I didn't really like the vertex and fragment shaders before. But when compute shaders appears, that was very natural for me, because I didn't have to create an object to compute on. I can compute on buffers, and this is the key point. Compute shaders work on buffers that are on GPU side. Okay, so now how we'll start. So I assume that you already know a bit about the about simulations, and I will not talk much about them. I will introduce you to OpenFrameworks, and I will do this by two tutorials. So let's go to the website maciejmatyka.medium.com, and on this website you will find some articles from myself. One of them is GPU compute shaders in OpenFrameworks tutorial. So let's go a bit quickly through this one. And this is an introductory tutorial on using compute shaders in OpenFrameworks. So what is OpenFrameworks? So I need first to introduce you to the general picture. So the general picture is that shaders are working on GPU, but to run them you need to have some kind of API. And one of them is of course OpenGL. You can use DirectX on Windows and so on. But I was working with computer shaders before in OpenGL, and I must say it's not really very convenient. I didn't like it. So when I found that OpenFrameworks, a library, high-level library for graphics and media and so on. Let me play just video that shows what OpenFrameworks is capable of. Okay, so OpenFrameworks is a high-level library that you can download for free, and it has a community of people that are very helpful. And it's a C++ library for Windows, Linux and OS X, and also even on mobile for iOS and Android. So OpenFrameworks is a library that brings you to the higher level with Google Compute shaders. I must say it's very convenient, and it removes all the headaches that I had with OpenGL. So I will not go through documentation of OpenFrameworks, just introduce you to compute shaders with OpenFrameworks. So if you are not familiar with computer graphics and programming in OpenFrameworks, just go through some simple examples of it. It's very simple, and now I will show you on this example on Grace code reaction diffusion how does it work. So the Grace code, so this will be about simulation like this, so you will get pictures very similar to this one with some post-processing, but we will get directly the result very similar to this one. So I will skip the introduction and the video and just go through the tutorial. So first, what is compute shaders? You already know what the GPU is in my eyes. Okay. Now, how the simple program in OpenFrameworks looks like. So this is a very simple code actually. So OpenFrameworks, like a usual program in OpenFrameworks, expose OFAPP class. And this class consists of very usual functions, usual for programming with graphics and with some graphics user interface. So we have a setup method, we have an update, and we have draw. So obviously setup is to set up the things, update is to update each 60 times per second, and draw is to draw. And then we have of course this implementation. Now the main file is like this, and we will not touch it in the tutorial. So we have a main function, we open the OpenGL window, okay, we create it here, this is the moment that the window appears, and then we run the app, okay, we create an OFAPP object and pass it to the OF run app, and that's it. So what do we want to write? We want to write first the reaction diffusion system. So if you click, don't click on Wikipedia first, it's not very nice. You could click on Carl Sims website. This artist, Carl Sims, is famous of other things, but one of these very nice articles on the web is about the reaction diffusion here. So in a very nice way he introduces these two equations. And so these basically are some discretization of simple discretization of partial differential equations, and we have two buffers. One is AB and one is A prime B prime, and those buffers are swapping each other. So we calculate the whole thing in a ping pong manner. That means in the even steps we calculate A prime and B prime. In odd steps we calculate A and B, so they exchange. On the right hand side everything is known, so it's very simple. We just calculate Laplacians with some approximation and then calculate directly what is here. So this is very simple, and I will not introduce more. Just read those websites if you want. You can also play with it online. Okay, so these are equations that we will use in our code. Laplacian I will show later in the compute shader implementation. So let's go. We have this simple class that we want to update now. So first we will create our buffers. Buffers are important because they are stored, they will be later stored on GPU, and we will perform some operations on them. I will use CPU arrays to initialize buffers on GPU. This is because I have a lot of memory on CPU. I don't care. If you want to optimize, you can skip this and do it do it in more optimized way. But I will first have all the buffers on CPU, then I will create OF buffer object. So this is an object actually from OpenFrameworks, and this I will create for A1, B1, A2 and B2, just to do these primes later. Now we have our system of this size, and this will be directly one-to-one to the pixels on a screen, but of course you can use lower or higher resolution, no problem, and just scale the final texture. Okay, now we can initialize those arrays, use A1 CPU and B2 CPU, those guys, and allocate GPU memory. So let's initialize first. So on CPU we'll just put some ones into A1 and A2, and we'll put 1 or 0, depend on this random number, into B1, and put 0 into B2. Now we allocate buffers on GPU side. So on GPU side we'll just use the allocate method of A1 object. So A1, I will reckon this is buffer object, and it has the method allocate. So we allocate this size of memory, initialized by this array, and just use the static draw. You can use dynamic draw here. Actually, if you know what is the difference, really let me know in comments. But for me, it was not much difference. Use GL static or GL. This is like just an information to the driver that we will use this buffer for dynamic or static drawing. Now now let's follow. Now the buffer bindings. So what are bindings? This for bindings. Sorry. So the buffer bindings are a headache for beginners in OpenGL. Actually, it was for me, but it turned out to be very, very simple. So you have to think of binding scheme as an idea of connecting your buffers that are actually, those buffers are on GPU, but so that picture should have this frame here. But anyway, so the buffer is bind into some number that is like a slot on GPU. So on GPU you have some static slots, 0, 1, 2, 3, 4, 5, 6 and so on, but each of them has a number, and you can bind a buffer into this slot. So this is like giving a name. And this is important because then if you put like A2 into buffer 1, then each of the shaders that you will run on GPU will see this first buffer as a A2. So from this point of view, you can just reconnect these wires here to change A1 with A2, and this is what we will do later. So this is called binding. And binding is simple. You just use the bind base function, and then put what kind of buffer you will, or what kind of data you will bind into the slot number, and you put the slot number. So you see we have A1 on 0, A2 on 1 and so on. Now because we want to see our simulation, we will visualize results as a texture. Now how to do that? So first we will create a texture with a Polish name textura. Okay, so the texture is OF texture. So for people that got used to program in OpenGL, you will see how simple is that in OpenFrameworks. We just create textura, and then we allocate it of the size W and H, and then textura will be binded. So we do binding as an image into number 4. as a just write only. But anyway, so we have 4, so we'll not read from the texture, we just write to it. Okay, so 4, why 4? Because we already did 0, 1, 2, 3 and 4 is the next empty number. You can use anything that your card allows you to. Okay, but just remember, we have 4. And then textura will be drawn on the screen in point 0, 0. Okay, so now the culmination point, now we actually go into the shader stuff. Now the shader stuff starts with creating a shader. So we do the OF shader of the name shader. This is just simple. Now the shader will be set up from file. And this again, in OpenGL or your program, you always had to create your own function to like include shader into GPU. But here we just use the setup shader from file function. We put our compute shader of this name and we link the program. So now all the magic happens here, because if your program has, if your shader has any errors, then when you run your program, it will try to link it on GPU and compile it here, and this will bring some errors if some mistakes are done here. Okay. So now we go further and go into the ping pong scheme. So this is what I told you before. We will compute A1 and B2 from A2 and B2 arrays, and we will swap them. So then A2 will become A1 and so on. But do not make it complicated, we just reconnect it by using here the ping pong scheme. So the ping pong is like this, so we'll use bindings. We introduce some static integer. C, static means this will be run only once when the update will be called, and then C will be 1 minus C, so 0, 1, 0, 1, 0, 1. So if C is 0 or 1, then the A1 will be binded into the 0 or 1 slot, and then A2 will be 1 or 0. Then B1 will be 2 or 3, and B2 will be 3 or 2. Okay, so that means we will swap ping pong, ping pong, ping pong. Okay, then to run the shader, we need to introduce the working groups concept. So when you put your task in your shader on GPU side, you have to tell GPU how to run it, in what configuration. So I recommend to go into NVIDIA or CUDA documentation for this. It's very nicely introduced, or even to Chronos to read more. But anyway, to understand what we do is, in simple word, is that our compute shaders, instances, are grouped into working groups, and each working group is run in parallel. And because 90% of the problems in computer graphics or in science is in 1, 2 or 3 dimensional in a regular grid, then GPU is organized in a way that it can get groups of this and this size. So it can have 2-dimensional working group, or 3-dimensional, or 1-dimensional. In our case, the working group will be 2-dimensional, and its size will be W divided by 20 by H divided by 20. So this is the number of threads that will be run in parallel each time the GPU will run our program. So basically we use the function which is called dispatch compute. It's a funny name, I would put here run on GPU. But okay, we have the dispatch compute, and this shader just run like this. We do shader begin, shader dispatch compute, we provide the working group size, so the Z direction is 0, and the shader ends. And that's it. So yeah, that's simple. And now, last but not least, we implement the compute shader. So our compute shader again will implement the Gray-Scott reaction diffusion problem. And so we start with empty shader. So this tells you what version of OpenGL we use. So 4.4 is the lowest possible, and we have the void function main, void main. And this is very similar to C language. We use GLSL for implementation. So first we do all this binding stuff. So you see the binding 0, the one we already put, is the float a1. And just remember, this name a1 has nothing to do with the name on CPU side, but it's just happened that it's the same. You could put a1 GPU here if you want. But anyway, so if we bind anything here to 0, it will be seen as a1. Okay, and so on. So this is like this is what the GPU side see, and these numbers are what the CPU side was putting as a slot number. And the picture was 4, you remember, the fourth one. And this was uniform right on the image to the image. So this is the name, okay, the long type for the texture. And now the layout of the size of the working group, and you see the number of working groups is 20 in X and 20 in Y direction. The size of working group was W divided by 20, you see? Where was it? Oh, here. Okay, that was the size. And this is the number of working groups. Okay, now let's implement the main function. Oh, no, not yet. First we put some periodic boundary conditions helpful function. So this is the periodic function. It gets the X and the limit, and then if the X is lower than 0, we add the size, and if it is larger, then we subtract the size. Okay, so this gives you the periodic boundary conditions. I also use some color scheme. The color scheme is very nice for visualization, because the result will be coded in a floating point from 0 to 1, and of course you can just do some simple shading with 0, 1, but it's not very nice. So I use the concept introduced by Inigo Quiles, so you can go to his website on which he has a lot of very nice articles, and one of them is about palettes. So how to encode a color, but just by using simple 0 to 1 numbers. So from 0 to 1 you can get this gradient, okay? And Inigo uses it for very nice visualizations in his work. So I also decided to use it. It's very nice and simple. So I put a number, and in the result I get the 4-dimensional vector, so RGB1, okay, of the color. And this is the palette that I chosen for this particular example. Now we will use the now we will implement the shader. So how does it work? So the shader knows the I and J position. I mean, we can read it from the GL global invocation ID, and this is X and Y position in your grid. So if you run the shader in the way that I put here, you can always know in which position on your array you have to compute anything. Now I use this ugly way of putting constants, because of course you can use uniforms and then just put uniform into the shader, but I will not go into the details. I just hard-coded the size of the system. Then I calculate index. So this is because I use one-dimensional array to code two-dimensional data. And this is because it's much easier for later to implement, for instance, the fluid solver, because I have like 18-dimensional table there, and then using the normal table would be headache. It was much easier with this. Then we have some constants. These constants are for just for Gray-Scott direction diffusion. And then we have this, what I do is I recalculate the constants depend on the position on a screen. So if this is age, it goes from left to right hand side with from 0 to 1, and then half, so from 0 to half. And then I use this age to do linear mapping of the f and k constants, so from this to this value, okay? And this gives me some nice gradient of the Gray-Scott behavior. Now I calculate neighbors, so I do I plus 1, I minus 1, j plus 1, j minus y, and I using periodic function, and then just find the indices for them. If having neighbors, I can calculate Laplacian, okay, at my point. So Laplacian is basically approximated by 1, 2, 3, 4, 5, 6, 7, 8 point Laplacian approximation. Then I use Gray-Scott model, and this is all. So this is the Gray-Scott. And then I visualize things. So basically I have the A and B, which is read from our new calculated data, so from the fields, and then just some mapping. This is hard-coded to obtain nice result, and then I color it. And having it, I can store the image on in a texture, and that's all. That's the final code. Is like this. You can just copy it from the tutorial and run it, and this is the result. So I will not. Okay, you can click here and see from the YouTube, but YouTube put YouTube put some advertisements. So let me play it live. So this is our Gray-Scott. This is the first example I have for you. So now if we run it, make. So in OpenFrameworks we do make and then make, run, release. Okay, so if we run it, this is the result. So it goes like this. We can see the some species that are evolving in time. There is some reaction happening. So depends on the position on the screen. The parameters of our system are different. So you can choose like this point and choose these parameters and see do the simulation for this particular parameter in entire system. This is not a problem, but now you can see the nice behavior. It changes from place to place. Okay, so this is the Gray-Scott. Okay, so let me know. It happens in real time. Okay, so you could have the you can have it even in larger resolution. Now I will move to the beginning because I copied this tutorial from my blogspot article to here to Medium, and in Medium I wanted to have a different picture, so I chosen this one, and this is not one-to-one what I presented in tutorial, but it's much nicer to see. And why does it look like this? Because this is the so this particular example is also Gray-Scott, but it's with bumping. So I found some very nice technique of bump mapping. So this technique is technique that can change your two-dimensional data into semi-three-dimensional picture just by using some simple lighting. So we calculate normal in each point, and this normal is used to do some simple lighting. Run, release. Okay, and now we have this behavior. So you see also just the color is different than here, but anyway, so it's the same. It's direction diffusion with Gray-Scott on GPU, and it happens with some post-processing with bump mapping. So it looks like this. Okay, hope I just show it for you to give you some motivation to work with that. It's really very nice technique that it works in real time. Now let's go into the fluids. So the fluids are in the second part, and it's everyone is showing two-dimensional, so I decided to do three-dimensional fluids. So it's this tutorial shows you the how to implement real-time simulation of 3D fluid flow, and this is the result of the tutorial, and you can basically go through it and implement by yourself. I assume that you know what Lattice Boltzmann method is. So this tutorial and my talk today is not for showing you how to implement the Lattice Boltzmann, it's how to implement it in compute shaders. Let me just go back into the first one first, because I also show the this two-dimensional Lattice Boltzmann you can see in the movie here. Okay, and this is the second part. Okay, so how this tutorial goes? It goes in the same way. So I show you the result and then start. So we start with simple OpenFrameworks application that is empty, and we put everything that is needed in Lattice Boltzmann. So basically the size of the system, all the constants, so like definition of the grid, some helpful constants and the CPU data, Then we do all this periodic stuff, and we initialize the data on CPU, allocate GPU buffers, do the binding. It's much more, but it's the same as it was before. Then we implement the compute shader, so we put the same constants here, so you can always use uniforms. Remember, I just did it because it was simpler and quicker for me. Then we do bindings, okay, and then we implement our LBM, so it's usual stuff, okay. You have some here the difference is that we have I, J and K, because this is the three-dimensional stuff now. And then the Lattice Boltzmann is implemented here. It's so I will not go into details much, but we just calculate some macroscopic variables, okay. Then we compute the updated velocity, and then do the collision and streaming, which is just those two lines, okay. Depends whether your next neighbor is boundary or it's a fluid site. And then we can calculate this like relaxation towards equilibrium with the streaming step at once. Okay. If you play with the code, you can change this one, tau, from 0.5 to 1 point something, and then by using this, by changing this, you can change your Reynolds number, for instance. Okay. Okay, let's go further. So we dispatch the compute shader, so we have the shader, we have the setup, we have to set up it and just do the bindings and then run the shader. Okay, the bindings are done on those two fields. This is F0 and F1. F0 and F1 are 18 dimensionals probably, because I use 15 velocity directions, so this is 18th multi-dimensional table array coded in one-dimensional one, and we just do the F1s to F0, F0 to F1. So it's even simpler than in Grayscott. The visualization was tricky for me because I had to define particles to see the flow actually. Without particles, that is very hard because we have volumetric data of velocities. So I use particles of this structure, its four-dimensional position and the color. I will use vertex buffer object to plot the particles and initialize them on CPU in the standard STD vector. Then the buffer object is used, the particles buffer, okay, on the GPU side. Now the particles are initialized on CPU just in random positions, and then allocated on GPU, and the vertex buffer object is set by using this buffer. And then we bind the buffer into number 6. Okay, and then the particles will be advected using these simple equations. So these are linear approximation of the movement of a particle in the flow field so the particle is massless. It doesn't have any mass. And then the particle shader is like this. We just have some, again, palette to code the palette. We have the same structure as on the CPU side. There are some bindings we use, the periodic function, and then there is some random, copied from Stack Overflow, I guess. We just take some, so the random will be initialized by UV. It's actually tricky to do random in compute shader for me, so I used the position of on XY to compute new random number, and I use them for to put the particle in new position when the particle goes away from the system. Now the main function, we have XYZ, the size of the system, again hard-coded in the code. Actually, yesterday I was working with another shader and I already put uniforms, so the next one tutorial in next year will be with nice uniforms, I guess. Okay, so then we have the position of the particle, we compute the number of the grid in which the particle is. It's all very approximated, it's just for visualization, otherwise you need to spend some more time on doing this really precisely. Then we compute the index of the position in our grid. Then if the position is not equal 1, so if we are in the fluid, we just advect. But if not, then we have to go. This is because I will use some obstacles, and if the particle goes into obstacle, and this happens because we use some numerical method of some limited accuracy, then we have to find a new position for particle. Then if particle goes away too much, we also do this and so on. And we use the periodic. So if we move if we move away from the system somewhere, then we need to do periodic boundary conditions in each direction. Then so you can play with that, you know. Anyway, so then we get our velocities, and these velocities will be used to code the color. I will not go into details because it's so hard coded that I don't even remember why I put all this stuff here. In the result of these functions, we just get the new vector of color, and we update particle array on GPU. So we use the X, Y, and Z position, and then put color, and that's it. So then we can have the whole and not that's it, because we have to compile the shader on the CPU side. Okay, so shader particle is here, and then we set up from file and link it, and that's it, and we dispatch. We dispatch the compute, and here is the size of the of this. Okay, to draw the particles, we use the VBO, so the vertex buffer object. And for this we need some lighting. I don't know if the lighting is important here. Anyway, we use the EasyCam, and the EasyCam will be the camera, and this is because this is three-dimensional. We set the drag, we set the distance of the camera. I put some functions here, don't even know if they really matter. If they're really working here. Okay, we draw the stuff. So we set the background not to be white or anything. We clear with black. We start with camera, and then we set up the drawing. And the drawing is like this. Just translate the size of the point and enable blending, and then draw. VBO draw. And this is fun, nice, because we draw directly from GPU. So you remember this picture, we don't have to copy from the CPU to GPU and then draw, as it would be in the OpenGL 1.4, but we just work here, run the shader, and then plot, okay? And this is quick. Then I use some very naive and not very fast way to draw the obstacles. So if our like a flag array on CPU is equal to 1, that means we have some no slip boundary condition. I mean the node that is not fluid. Then if one of the neighbors is fluid, we draw the small box, and this will give us the obstacles. And this is all interactivity and complete code. So this is the complete code. I just use key pressed to let the user to actually, okay, this was here before, to let the user to add some obstacles. So if the key is pressed, any key, so I don't check it here, then we add some sphere into the system, and then after adding it, we can transfer the data to the CPU. Funny thing, I use the dynamic draw here, even though I don't use the F on the GPU to draw it, but anyway. So I would change it to GL static draw now here. Okay, and the particles shader is like this. Now it's all. Okay, so this is the complete code and the result. Okay, but do not go. Let's not play here. I will run it in real time. So this is three-dimensional one. Let's go into 3D now. 2D you can find in my first tutorial. There is also a link on 2D, sorry. Okay, so if you are interested, go to my YouTube channel and you will find two-dimensional also. And this is three-dimensional flow. I will add some obstacles just to make it more visible. And now, okay, now the particles should be visible like this. Okay, so you see now the three-dimensional fluid flow, just like that. Yeah, So actually it's not very simple to put some it's not very simple to put some visualization in 3D such that you see the three-dimensional effect, because my flow is volumetric. That means we have the volumetric data in the result. There is no free surface I could extract. So with free surface it's much easier to visualize. Actually, I will show something in a second. Okay, so this is three-dimensional flow, and that's it. I will not go into more about the implementation of other things. I will just show you something at the very end, which actually was my failure. So I wanted to implement also the multi-phase flow. So for multi-phase, I used first two-dimensional Lattice Boltzmann, and two-dimensional was pretty nice to implement. This is the result. This is also a fluid flow simulation, but with the approximation of two phases. So we have single component multi-phase flow, it's called. That means because of the difference in density, this happens that those droplets appear, and there is some kind of phase transition, you see. It happens in real time also. So this is an implementation of multi-phase flow. Anyway, so this happens on GPU also, and I wanted to do the same in 3D, and you can imagine how tricky it is, because the problem was that with three-dimensional multi-phase flow the result is volumetric. That means we have the density. So in order to visualize it, I had to do something like this, because so you can imagine that if you have three-dimensional flow, which is like this, okay, and you have your density, which is high here and low here. So in order to visualize it, you have to either extract your surface, and you can do by using I don't know what was the name, right, no remerging. It was I forgot the Merging cubes algorithm. Okay, you can use Merging cubes, but to do it on GPU and so on is quite a lot of work. And I decided to do something else. I decided to use the ray merging kind of technique and do volumetric ray casting. So that means to create a picture, basically I put some rays and I go through my system and just compute some how much of density is in my ray. And also I do some scattering of light and so on, and all this stuff was a headache for me because I had like 1 or 2 days to do that, and it was before the workshop in Kraków, and I didn't really do it before like this, so I had to really do a lot of not optimized ways. So for instance, I go just by using the same step for each ray. I don't optimize anything here. I even go with this rays up very long if the ray is not hitting the cube, which is obvious to anyway. So that is very slow, and when I ran it the first time, I realized that it's not very fast and I didn't like the effect, and the effect was really like someone told me, thank you for that it looks like some nice thing which is 16-bit, okay, computer result. And I even would say it's 8-bit. So, and because Robert, organizer of LBM in Kraków, is from the demo scene, so I decided to do a demo scene kind of presentation for it, and let me just play it for you, and that will end our tutorial. And this is multi-phase flow in 3 dimensions with volumetric ray scattering, light, everything, so on. A lot of improvisation from my side, not really physically correct visualization, but somehow looks like, okay. Let me play it for Robert, and this will also an invitation, so for you to be in Wrocław. So see you in Wrocław, and that's it. Okay, thank you very much. Thank you for N1K0 for the very nice music and to allow me to use it, because it was used in the some previous demo for ZX Spectrum before. Remember to subscribe if you like the things happening here on my channel, and see you around. So have a nice day.